Cool. Hopefully they can hear me. I guess we'll find out. So this would be for like discretized distributions. So in other words, say we had like, you know, like only a couple of masses in a region, then this is okay, right? We're just summing up a few pieces. Um, but as soon as we have like a solid object, the number of atoms is so large that this definition goes from being discretized to being continuous. And so then we get that XCOM is 1 over big M, the integral of XDM, and then it'd be YDM and EDM, and then this one doesn't seem to be generalizing into, yeah, no, just keeping it like that. Keeping it moving. So now we've got Newton's second law for a system of particles. Have we talked about this yet? Okay. So have we talked about momentum yet? Okay, do you guys understand what momentum is? A little bit? Okay. Have you seen force written instead of F written as dp dt? Have you guys seen that yet?
The derivative of
Momentum, yeah. And so from this definition, you say that that's equal to ma. Then if you were to integrate both sides with respect to time, then this would just become dp, and over here be ma dt. Pretty cool with that. And from there, we would see that if we integrate the infinitesimal of momentum, we would get to the total momentum. And over here, so if we take a derivative with respect to time of velocity, say, what are we going to get?
acceleration.
Right. And so then going backwards, if we take an integral of acceleration, it would be velocity. This becomes mv. So there's our momentum definition derived.
And this might be a silly question, but like, what is infinitesimal?
Yeah, sure. That's a great question. So,
Yeah, he says that all the time.
so have you taken Calc 1?
Yeah.
Calc 2?
Yeah, I'll take it right
Okay. So good. So that's a great question. So do you remember when you were learning about integration for the first time?
now. Yeah.
And you have some curve, right? And we want to find the area under the curve from say 0 to a. And so beforehand, you were doing it as like a discretized sum, adding triangles. In other words, it would be like something like this, and you would take the width of the function, and then times the. You would basically turn these into rectangles, and the width of the function is something that you set, and then you would take the height of the function to be where the function was at that point. So if you take this and you shrink these rectangles down as small as they can go, that's the smallest possible x distance, we would call that dx. So that's an infinitesimal,
Okay.
right? And so like dt is like the smallest amount of time.
Got you.
And so back over here, dm for mass. Yes, exactly. And then dp is infinitesimal for momentum. And then so the idea is that if you integrate over the infinitesimal, you're doing an infinite sum of all those tiny little pieces, so you end up getting the whole piece.
Cool. Thank you.
Yeah, of course. We cool with if I erase this, guys? Just gonna stick to the side of the board because I've got the angle set up now. Keep moving it. So, keeping it moving right along. Have we talked about impulse? So if you say that this is equal to the integral force with respect to time T0 to T1. The left side of our equation is going to give our change in momentum here. And the right side of the equation is going to be what we're going to call the impulse. So it measures the magnitude and the duration of a collision force. So in other words, like if I take two rulers and I smack them together, there's this thing called impulse, and that has to do with how long they were touching each other and how much of a force they apply to each other, and that determines their impulse. So it's useful because there's this thing called the linear momentum impulse theorem, which states that change in momentum is going to be equal to the impulse. So in other words, momentum is one of these things that's conserved in systems. And so the only way that you're going to get a change in momentum is if you apply an impulse to the system. Right? So like if I have a ball that's rolling with some momentum, the only way that I'm going to change its momentum is if I smack it with something else effectively and put an impulse on it. So So now we have a conservation of linear momentum. So I'm just going to read from the text here. Suppose that the net external force and thus the net impulse acting on a system of particles is zero. In other words, the system is isolated. And that no particles leave or enter, the system is closed. Then putting F net equals zero into this equation. If we say that F net, like we had defined it before, is dp dt, then if we say that F net is equal to zero, then that means that dp dt is equal to zero. And so what does that mean? What is that telling us? Well, what does this represent in non-math terms? Whole thing.
Oh. So like impulse versus time?
So P is going to be our momentum. And so what is the derivative measure for us?
Like absolute value?
So so say you have some functions, right? And I found the derivative at that point.
Oh, like the instant time. That like
There's like a change in time.
Yeah, good. The rate of change. So if our rate of change of momentum is zero, that means the momentum is not changing. It's a constant, right? The only time a derivative of something is zero is when it's a constant. So this tells us that momentum doesn't change if there's no external forces. And so what that tells us is that P is constant in a closed and isolated system. If no net external force acts on the system of particles, the total linear momentum of the system cannot change. Okay. This result is called the law of conservation of linear momentum. And it's really helpful in problems. You remember how when we were doing conservation of energy, you could solve things like how fast the block was going at the bottom because you knew however much energy it had at the top of the incline, it could not have any more kinetic energy than that. So you could set those things equal to each other and start solving things. It's the same kind of deal with this. So the idea is that if you know the initial momentum of a system, Pi, you know that that has to be equal to Pf, if we're assuming conservation of momentum. And so yeah, real quick, I'll just caution this because the book does as well. Don't confuse conservation of momentum and conservation of energy. They don't both have to be true at the same time, right? So there's certain problems like this says where momentum will be conserved, but energy is not conserved. So don't feel like they have to be conserved at the same time. So now we'll go with inelastic collisions in one dimension. So the idea is you have two bodies that are going to have a collision in one dimension, and we're going to be in a closed and isolated system, and we can write out the law for conservation of linear momentum, which is that you would just expand this basically and say that P1 initial plus P2 initial equals P1 final plus P2 final. And like the book says, we're going to assume we're in one dimension, so we don't have to carry around these vector hats anymore. And so we're just going to we're going to write out the actual definition of momentum here. So we've got M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. So there's our equation. And so, like the book says, if we know like certain values like the mass, maybe the initial velocities and the final velocity of one, then we can solve for the velocity of the other. So the idea is, say you had, let's just do a quick problem because we're just about out of time. So say we have two pool balls. Good old billiard ball problem. So here's ball one, here's ball two, and let's say that ball one is initially at rest. And we're going to send this cue ball flying in at, say, I don't know, 5 meters per second. And each of them have a mass of 1 kilogram. And so essentially what we can do in this problem is say, okay, let's say after they strike each other, so they're going to hit each other, and then they're going to bounce off in opposite directions. So, so say I tell you that the final velocity of 2 is 3 meters per second. I want you to solve for the final velocity. Okay. Anybody got any ideas of how we would do that?
Just take the equation and then write everything you know, and then just have to solve for what V2 final will be.
Yeah, exactly. So we're going to set up conservation of momentum. P initial equals P final. So M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. And so right off the bat, since our initial velocity and our second mass was 0, that term will go away. And so now we'll have M1 V1 initial equals M1 V1 final plus M2 V2 final. And so what we're looking for is we're looking for that right there. So what we can do is we can just isolate that term. And so we'll have M1 V1 final minus M2 V2 final divided by M1. That should give us V1. And so let's just see. So I made it 1 kilogram to make things a little bit nicer. So this is 1, that's 1, that's 1. So it'll be V1 final minus V2 final. Or sorry, V1 initial. So this is going to be 5, and that's going to be 3, and so 2 meters per second. All right, gentlemen, we've hit 5. So any other questions?
Not for today.
Okay.
Oh, was it from 4 to 5?
Sorry.
Was it from 4 to 5?
4:30 to 5:30. Oh.
I was wondering that. I was like, I guess.
I was thinking in my head. I was thinking in my head. I was like, it feels like that went by so fast. Okay, great. We still have half an hour. Okay, that's awesome. I was like kind of bummed. I was like, man, we didn't get to talk about it. All right, so okay, that's great. You guys all had a long day.
I thought it was 4 to 5 for a second.
I thought maybe he had somewhere to be. I was like, maybe he has to like leave early today.
Elastic collisions. So, okay, let me go. Yeah, let me go ahead and explain the difference between inelastic and elastic collisions. So, a completely inelastic collision means that the bodies stick together, right? And so the idea is, think of it like a car crash. I hate that that's an example, but it's a good one.
Like a photo in the textbook. I was like, that's kind of great.
Yeah. So the idea is that if you have some car, some guy, made too many trips to the liquor store, and he's driving on, and there's another car just like sitting like at a red light, just minding their business, and they're at rest, and then we got the initial. Let's say he's going like 65 meters per second. I think that's like 140 miles an hour or something like that. And so they're going to hit, and so he's got 1 mass. This car's got 1 mass. And so the initial equation is going to be, if we set it up, it's going to be P initial P final. So what are we having initially here? Well, initially all of our momentum is in car 1, right? So all we have is M1 V1 initial. And so what do you guys think that that's going to be equal to? Let's say this car's at rest. Sorry, this car's at rest. He's going to smash into it. It's going to be a completely inelastic collision, meaning they're going to stick together and move together. So what would the final momentum be then?
Would be M1 plus M2 V2
So we're going to call the velocity when they move together as just big V,
Okay.
because it's going to be a total velocity. And so based on what the initial velocity is and these masses, you could solve for the final velocity. They might say, here's the final velocity, figure out what the mass of the second car was. You know, you got everything you need in this equation to do that. So stuff like that. Now, elastic collisions are ones that conserve kinetic energy. So a perfectly elastic collision. So
Is there a difference between perfectly elastic and just elastic collision?
yeah, so the idea is that so there's never physically there's no such thing as a perfectly elastic collision.
Okay.
It's an idealized situation, right? Because no matter what, when two things collide, there's going to be some amount of dissipation of energy due to heat, and so kinetic energy would not be conserved in that case.
Okay.
And so they say perfectly elastic because that allows you to solve problems without having to worry about things like heat.
Okay, so if they say that, you're not factoring in like heat or like they said like noise also is like
Yes.
dissipation. Okay.
Yes. Yeah, because if they make sound,
Okay.
it takes energy away from the system because the sound waves have to displace air molecules, and that takes away energy from the system.
Okay. Because I saw in the textbook, I didn't know if that was like a big difference or if that was just like a writing here.
I mean, I guess it would depend. I mean, if you had two jets going at like the speed of sound,
Yeah.
probably would make more of a difference. I mean, you could calculate it, but it would be complicated. I wouldn't want to do it. That's one of those things you just say, no, we're gonna assume it's negligible and hope that it is. But so with these kind of problems, you can do different things like with them bouncing off each other, like what we were doing with the pool balls. And but the condition is that the kinetic energy is conserved. And so, in other words, how the book says is, of course, we have. Let's see. Yeah, they're doing pool balls. So, two bodies before and after they have a one-dimensional collision, like a head-on collision between pool balls. A projectile body of mass m1 at initial velocity v1i moves towards a target body of mass m2 that is initially at rest. So just like that scenario we were talking about. We're going to assume it's closed and isolated. That's pretty much always going to be the case unless you like are accounting for friction and stuff. Not okay. I will say this. Let me say this real quick. I don't know how complicated it would get for you guys, but there would maybe be a scenario where they want you to calculate the work done by friction and say, you know, they might say it's an elastic collision, but it's not perfectly elastic because friction took energy away from the system. Using work and energy, find out how much energy was taken from the system, because that wouldn't be horrible. Okay. Let's see. So we're going to assume it's closed and isolated, and then we're going to say that the net linear momentum of the system is conserved, and we're going to write the conservation like we had up here before as M1 V1 initial equals M1 V1 final plus M2 V2 final. Right, because our second mass was at rest initially. So that's our conservation. And so if the collision is also elastic, then we're going to say that the total kinetic energy is conserved. And then we can write 1/2 M1 V1 initial squared equals 1/2 M1 V1 final squared plus 1/2 M2 V2 final. Quick note, you may see, I don't know if it's something that's done in 201. It is done a lot in upper mechanics. You can write kinetic energy is this. So I don't know if you can see, but the momentum is kind of nested in there. And so it's a shorthand to write the kinetic energy. Just be aware of that, because I mean, I could see maybe Dr. Davis throwing you a curveball like that, and you're just like, what the hell is P squared over 2M? But if I'll convince you real quick that if you do the momentum squared, it's M squared V squared over 2M. One of the M's cancel. 1/2 V squared kinetic energy. So that's just a shorthand way of writing it. You may see it, you may not.
Okay, that's good to know.
All right. So that now gives us two things which are helpful, right? Because there's different things they can give you, and there's different ways that you can solve for it. They might tell you the kinetic energy is initially this. Find the final velocity in the second one. If this one has a final velocity of something. I mean, they could tell you the initial energy, the final momentum, and then ask you to solve for everything else. I'm pretty sure that's all you need to solve. So, yeah. Okay. Let's see. I mean, a lot of this stuff is just, understanding. Oh, well, this gets tricky. So this is a good problem. So you could also have systems that have changing mass. So that gets a little bit. I don't know. Have you guys looked at anything like that?
The rocket one,
Yeah.
He did that like on Friday in class.
How did y'all feel about that? Not good. Okay.
It's pretty complex.
Okay. Let's go through that one. Because we still got 20 minutes. So I'm just gonna follow the derivation given in the book here and try my best to. Hopefully the book didn't change its notation from the 10th to the 12th edition, and I'm using, and Dr. Davis used that as well. Because the idea, right, is that, well, I mean, the best way to think about it, right, is that the rocket is losing mass, and so if you want momentum to be conserved, then you would need the velocity to increase. That would be my initial assumption. Okay, so let's see what the book says. So far, we've assumed that total mass remains constant. Sometimes, as in a rocket, it does not. Most of the mass of a rocket on its launching pad is fuel, all of which will eventually be burned and ejected. We handle the variation of mass of the rocket as the rocket accelerates by applying Newton's second law, not to the rocket alone, but to the rocket and its ejected combustion products taken together. The mass of this system does not change as the rocket accelerates. Assume that we are at rest relative to an inertial reference frame, watching a rocket accelerate through deep space with no gravitational or atmospheric drag forces acting on it. We're going to let big M be the mass of the rocket, and we're going to let V be its velocity at time t. So we got big M, that's going to be our mass of the rocket. And we've got just a little v. So, okay, this is good. So the idea is that here's our rocket. And as it goes at some speed, v plus dv, we've got m plus d and minus d. So our system consists of the rocket and the exhaust products released during the time interval dt. The system is closed and isolated, so we're going to assume that momentum is conserved during this process. So just like before, we're assuming P initial equals P final. So we're going to rewrite as big M times V is equal to minus dm u and I think this is the decreasing mass and the velocity of the exhaust. That would be my guess. Yeah. So the minus dmu is the linear momentum of the exhaust products released during the interval, and then we're going to have m plus dm times v plus dv. So basically what this is, right, is it's the mass of the rocket times the velocity of the rocket, but allowing things to vary with time. Here is the exhaust velocity and its mass. And so it's negative because it's going in the other direction. So we want to simplify this thing by using relative speed between the rocket and the exhaust products. So we're going to say, so we've got v of rocket relative to our frame of reference. So I'll put with an F there. And then that's equal to the velocity of the rocket relative to the exhaust products. So V of R relative to products and plus the velocity of the products, V of P, relative to frame. So you guys covered relative speeds last couple of months, hopefully.
Yeah, we did it a little bit. So I'm guessing when you measure that, you're talking about like you're using the speed of the rocket as the frame of reference, or the velocity of the.
So at the beginning of the problem, we stated that we are at rest to an inertial frame,
Okay.
and watching it accelerate. And so let's see. So in symbols, the book says we're going to write this as velocity of the rocket relative to frame, which is just our v plus dv. And then the relative velocity, which is the rocket relative to the products, which is v relative, plus u, which we're going to say is the velocity of the products relative to frame. And so they're going to rewrite this in terms of u, stating that u is equal to v plus dv minus the relative velocity. And then we're going to substitute that into our equation there. So using the relative velocities is effectively an exercise in trying to find some algebraic trick that's going to help make things a little cleaner. And so we're going to substitute this whole equation in for this u term. So we'll have mv is equal to minus dm times v plus dv minus v relative plus plus dv, or sorry, yeah, n plus dm, sorry, and v plus dv. That's what we're working with. I'm gonna erase some of this and kind of move back over. So this is where we're at now. So I'm gonna go ahead and start cleaning it up. So we've got MV equal to minus DMV plus, or sorry, minus DMDV. Just expanding this out. Minus, or sorry, plus DMV relative. And then we can FOIL that guy. So it'll be MV plus MDV plus DMV plus DMDV. So right off the bat, that goes away. Everybody cool with that? So now we've got MV equals DM V relative plus MV plus M dV. And so, let's see. And then we'll just see one last step. We'll subtract this over, and we'll get dm v relative plus mdv equals 0. And so we'll move this over to the other side. So our final result that we're going to work with is going to be mdv equal to minus dm v relative. So now we're going to say that we're going to divide both sides by dt, and that makes sense, right? Because we want to vary this thing with time. Because right now we just have rate, we just have the infinitesimal change of velocity, infinitesimal change of mass. As soon as we divide by dt, now we have some rates of change. So now we have m dv dt, and that's equal to minus dm dt v relative. And so what we're going to do is we're going to replace the rate of change of the mass with r, but we're going to replace it with minus r to get rid of the negative sign, and that's so we can say that it's the positive rate of change. So just a magnitude, basically, of how much is coming out. And then does anybody want to take a guess as to what we're going to get on the other side? So we're here. So we're going to replace dv dt with what? Good. So this is big M times A, and then we're going to replace dm dt with minus r. R. So that's our first rocket equation. And so it says, notice that the left side, so I have them flipped around, sorry. RV relative has dimensions of or sorry, wait a minute. Book is confusing me now. Kilograms, seconds. Yeah, no, never mind, sorry. So our V relative has dimensions of force because this is a rate of change of mass. So kilograms per second multiplied by meters per second gives us kilogram meters per second squared, which is newtons. And so notice that. So this is effectively F equals ma for a rocket that we've derived. Um, and so it only depends on characteristics of the rocket engine, namely the rate at which it consumes fuel mass and the speed with which it is ejected relative to the rocket. So that has a fancy term that physicists came up with called thrust. And so the thrust is R V relative. Um, and it's represented with a T. And so if you rewrite R V relative as T, where T stands for thrust, then we get the thrust T equals M. And so now we want to find how the velocity of the rocket will change as it burns fuel. So that's the second rocket equation, and we should have just enough time to knock that out. Everybody cool if I erase this? So, let's see what that gets us. So we're going to start back at this equation. mdv is equal to minus dm v relative. And we're going to rearrange this such that we have dv by itself. So dv equals minus dm v relative over m. And then we're going to integrate both sides. Okay. So now we're going to clean this up a little bit. So what we're going to do, and this is where you guys see integration was actually invented for physics, and this is where one of those cases where you really get to see that. So what we're going to do is we're going to say that dv, we're going to let this integral run from initial velocity to final velocity of dv. And here on the left side, first of all, we're going to take v relative out as a constant because that's not going to change in our system. And we're going to let this run from initial mass to final mass. And if we do that, then what we have is we have 1 over m dm. So now let's just integrate both sides. So if we integrate dv, what are we going to get?
dv dt.
Close. So what is this? Unbounded, don't worry about the bounds, just the integral of dx. Good. Similarly here,
Just velocity.
it would just be v. Yep. And so since our bounds are v final, v initial, it'll be v final minus v initial, so we'll call it delta v. And how about on the left side? We're going to have v relative multiplied by what? What is the integral of 1 over m? That's okay. So that's going to be our natural log of M. And we're going to go from M initial to M. And so this is going to reduce to V final minus V initial equals V relative, the natural log of M final over M initial. Oh, did I miss? No, I did not. This should have a negative sign. Sorry about that. Which means with a negative sign here, we can flip these. So we'll have V final minus V initial is equal to V relative natural log of M initial over M final. Is everybody cool with that? Hopefully maybe that demysticized some of the a little bit rocket problem business.
Yeah.
I think what I'll end up doing is I'll probably go and really like work out the problem thoroughly on my own to where I can really add like a lot of insight to each part.
Okay.
I was, you know, it's not an easy derivation for sure, by no means. So don't feel bad that it's not sticking at first. My advice to you would be, you guys have your hands on textbooks?
Yeah.
Okay. I would go through the derivation a couple times on your own and see if you can kind of feel comfortable with it.
Okay.
And then we can talk about it again next week if you guys are still worried about it. Do me a favor. Go. Cut this video. See you later, Matthias.